My name is Daud Ahmed. In this lecture, we will talk about logistic regression. Logistic regression is a machine learning model or a machine learning algorithm that predicts the value of a binary target variable given one or more predictor variables. The target variable is represented by a y. Since it is a binary variable, it can have only two possible values, such as good or bad, healthy or unhealthy, obese or not. It is common to represent one of the values by a 1 and the other one by a 0. Y belongs to the set that contains 0 and 1. The categorical variables x1, x2 to xk can be either numerical or categorical or a mix. It is common to represent the predictor variables with the capital X as a vector. We have aggregated the predictor variables into a vector X. Logistic regression maps the values of these predictor variables to the probability of the target variable. This is the probability that y equals 1 given a particular sequence X, and this is the complement of this event. So this is the probability that y equals 0 given the sequence X. This is, let's say, the event A. Then this is the event A complement. So it is possible to write probability of event A as 1 minus probability of A complement. Another way to express the probability of an event is to write it in the form of odds of the event. The odds of an event mean probability whether the event occurs divided by 1 minus the complement, that is 1 minus probability the event does not occur. Probability and odds are interchangeable. If probability approaches 0, odds will approach 0. If probability approaches a 1, odds approach infinity. If probability approaches 0.5, odds approach a 1. So, working with odds is crucial to work with logistic regression. Logistic regression is an extension of linear regression. In linear regression, the target variable or the output variable represented by an O here is a continuous variable in the interval negative infinity to positive infinity. This is the equation of linear regression. O is the output variable in this interval. This beta 0, beta 1, beta 2 and beta k are coefficients, and x1, x2 to xk are predictor variables. We want to obtain an equation of logistic regression in which the variable on the left hand side is a probability from 0 to 1. That is, the left hand side has a variable that belongs to this interval, and that is actually probability that y equals 1, capital. To do that, we interpret this O as log of odds of the binary variable y and obtain this equation, this equivalent equation. To make it simple, we write all these values as a summation. We solve this equation to get probability that y equals 1, to get a variable, this one on the left hand side. When we solve this equation for p of y equals 1, we get this equation. This is the equation of logistic regression. The range is 0 to 1. And this is called the sigmoid activation function. Look carefully. sigmoid of x is equal to 1 divided by 1 plus e power minus x, and the interval of this function is 0 to 1. Same here. This is the sigmoid function that belongs to this interval, and the negative x here is this term here. We can write the sigmoid activation function with this sign, the sigma. If we know the k predictor variables and corresponding coefficients, we can use them to calculate the probability of whether y equals 1 or not. This is the plot for the logistic regression function. The logistic regression function is basically a sigmoid function applied on this term. The sigmoid function has the property that it always belongs to the interval 0 to 1. So it is one of the best choices for modeling probability. Remember that we are talking about the probability of the target variable equaling 1. Therefore, the plot of the target variable is restricted from 0 to 1. This is the curve of the sigmoid activation function. It is crossing the y-axis at 0.5. Remember that our goal was to map this probability to a 1 or a 0. Look at this function. If the probability that y equals 1 is greater than a specific value called t, then we predict y equals 1. T can be any value, like commonly chosen as 0.5. If the probability that y equals 1 is greater than or equal to 0.5, then we get a y equaling 1. Else, we get a y equaling 0. And this is our final result. The value t is called the threshold. On this graph, if this curve is greater than 0.5, then we map it to a 1. Else, when it is less than 0.5, we map it to a 0. Since it is always in 0, 1, it has an asymptote at the x-axis and an asymptote at the value, the line y equals 1.